Let's evaluate the sine of x divided by x dx. I don't know, you know, there are certain functions that don't have antiderivatives, not in closed form. I can tell you for sure that this second one in part B, e to the x squared, there is no closed form antiderivative for it. Sine x over x, I don't think there's one for that either in part A. So how do you integrate it? Well, you use a power series. That's how you do it. So let's think about it. What was the power series? And I'll go through the thought process for you to show you how to remember it. What was the power series for sine of x? It's a sine. You always start out sum. Usually it starts at 0 to infinity. I want you to remember it this way. The sine is an odd function. So the exponent better be odd. And you know how to generate odd numbers. You don't want to use 2n minus 1 because we're starting n at 0. So you use 2n plus 1 to generate odd numbers. Now furthermore, you just have to remember that it alternates. And the first term's positive. So to get it to alternate, it would be -1 to the, since we're starting at n equals 0 and the first term's positive, it would be -1 to the n power, right? Because that makes the first term positive when you plug in 0 for that exponent. And then it's x to the, what's the odd exponent? 2n plus 1. And then you divide by the same formula, except you have to factorial it, if I can make a verb out of that. That's it. And then that's, well, I mean, that's not the integral, but that's the sine function, right? Does everybody agree with that? Or does everybody see the thought process or understand the thought process? Remember, you've been told that the sine was an odd function forever since trig, right? Well, that's a good way to remember it. Oh, the exponent, if it's really an odd function, when you write it using a sort of infinite polynomial, that's what this kind of is, then the exponents better be odd, right? The exponents on the terms better be odd. Okay. Why don't I just divide both sides by x? Multiply both sides by 1 over x, same thing. And then if I bring the 1 over x inside, what do I get? Sum n equals 0 to infinity, -1 to the n, yeah. So think of it as dividing x to the 2n plus 1. If you multiply this in, multiply this straight across, you end up with a factor of x to the 2n plus 1 on top, x on the bottom, x to the 1, right? You keep, when you do this kind of division, you keep the base and subtract the bottom exponent from the top exponent. And so you end up with x to the 2n. Does anything else change inside after the sigma notation? Nah. Okay, so that was just scratch work over here. I didn't really need that. Does everybody see how I got that? All right, let's integrate. Integration's the easy part, isn't it? Okay, so just rewriting it, the sum n equals 0 to infinity with the integral symbol out in front, -1 to the n, x to the 2n over 2n plus 1 factorial dx, right? Newton loved Taylor series because, you know, the transcendental functions like sine x, cosine of x, they're kind of hard to grasp, aren't they? There's no formula where you're squaring or taking square roots or adding or subtracting, necessarily apparent formula anyway, to grab a hold of when you're integrating a transcendental function, like a trig function or natural log of x or e to the x. But when you write it as a polynomial, everybody knows how to integrate polynomials, right? So what do you do here? It still, you know, just recopy the sum stuff, the stuff involving just n. The only thing that matters is the formula with the x in it. How do you integrate x to the 2n with respect to x? Yeah, you use the power rule. You add 1 to the exponent, and then you divide by the new exponent, right? I'll put the 2n plus 1 here, but there's still a 2n plus 1 factorial in the denominator. Now, this was just an antiderivative. So what do I need? Plus c. We usually put the plus c on this side. Can we evaluate the integral from 0 to pi half sine x dx with an error less than 0.3 zeros and a 1? So let's say this. From the last example, well, let's go see what it was. It was this guy, right? I don't need the plus c, but it was this guy. So let me copy that. And what was that equal to? That was equal to the antiderivative. So how do I want to say this? I'll say it this way. We know that that's the antiderivative, so I'll say it this way. I'll say that this integral that we're asked to calculate is equal to this guy, except we have to evaluate it from 0 to pi halves. Would you agree with that statement? So in other words, I saved myself some work here because I found the antiderivative, which is that sum, in the previous problem. If I hadn't done that, you'd have to go through that part A of the previous problem again. Okay, now when I plug in pi over 2, what does that sum become? And then no change in the denominator. 2n plus 1 times 2n plus 1 factorial. And then that's evaluating at the upper limit. What about when I plug in 0? It's going to 0 out. So that, I suppose, theoretically, that's an exact value for the integral, right? But of course, if we want to use it, we have to approximate the value. So we're back to the alternating series estimation theorem once more, right? So let's do this. Let's use ASET, alternating series estimation theorem. All you really have to remember is to write out several terms and then break your calculator out. And then there's a little more to it than that, but let's start there. So use ASET, and let's just list the first few terms. What's the first term going to be? And you don't have to do any complicated multiplication. We can have the calculator do that. Is it going to be positive or negative? Positive, and then pi over 2 to the 1 power, right? So this would be over, yeah, just 1 because we're plugging 0 in here. So just over 1 right there. So I'll say that this series is approximately equal to, so what am I pointing at here? I'm saying this is approximately equal to, we're just going to take, we're going to sum a few of these. Okay. So whoops, is the next term going to be positive or negative? Negative. And now you've established the alternatingness of it. If that's a word, and you don't need to worry about plugging in a -1 to the end, right? Just remember it goes plus, minus, plus, minus. So then plug into the other stuff. It becomes pi over 2 to the what on top? 3 over, don't calculate it, just say 3 times 3 factorial, right? Okay, plus what? Pi over 2, well, is it just odd numbers that it's increasing by, the exponent? So I think we can not even look at the formula now. What's the next exponent going to be? 5 divided by 5 times 5 factorial. What's the next one? Minus pi over 2, 7 over, 7 times 7 factorial, I meant to write. Now, I might want to check that, and I'm going to check it by just looking at my old notes. I think we're going to want to go one more. So what would the next one be? Pi halves to the 9th over 9 times 9 factorial. So all I'm going to check is the last term. And if it's within the error bounds that I need it to be in, then I know that I'm just going to sum the terms that come before it, and that's going to be within my allotted error. That's all it is. Does that sound simple enough? That's all the alternating series estimation theorem says. Okay, so let's try it. You just have to type it in, right? Okay, let's put it in parentheses. Pi over 2, let's see, pi, there it is, divided by 2. Let's bring that to the 9th power. That should be pretty small, right? What do you have to be careful of when you divide? You better put in parentheses. 9 times 9 factorial. Where is the factorial button? Go to math and then left to PROB, probability. Comes up a lot in probability. And then close that parenthesis. Okay, so that's 4 zeros, right? And we only needed 3. So I think we're good. Okay, so we can say that this guy, this term is approximately, okay, 1, 2, 3, 4 zeros, then was it 178? Do I have that right? Yeah. And that's less than, I said it had to be 0.0001. So that's what you verify. You just make sure this is less than what you're told it's supposed to be. And it is. And so what the alternating series estimation theorem says is, hey, then, you can be assured then that the sum of the terms that come before it will be within that error, that allotted error, of the actual sum of all the infinite number of terms of the series. Isn't that crazy? And so that's what we do. We add those together. And so it would just be, what, pi over 2. Let me clear that out. Pi divided by 2 minus pi divided by 2 quantity squared. No, cubed. Not used to using a virtual calculator even yet. Divided by 3 times. You have to hit the buttons really hard on this. Okay, 4. Okay. Okay. It saves a little bit of time. I like that. Okay. So obviously on a real calculator with real buttons, it wouldn't take nearly so long. You get about 1.370, 1.371 if you round off. If you go to 4 places, 1.3707. Okay. So that turns out to be approximately 1.3707.